Hello everyone, welcome to Labtube. In this video I'm going to do question 13 from section 16.4. The question asks to evaluate the line integral for this vector field along the circle given by this equation and oriented clockwise. To evaluate that line integral, let me first recall what is Green's theorem. So Green's theorem says that if you have a vector field and you want to evaluate line integral of a vector field over a curve with these three properties. First, it is closed, the curve is closed. Second, it is a simple curve, means that it doesn't intersect itself. And third, it is oriented positively. If you have that kind of curve, the line integral is going to be equal to a double integral of this integrand, where f is given by p and q. So we have to find partial derivative of second component of the vector field with respect to x, partial derivative of first component with respect to y, subtract them, and then integrate. Okay. So in our case, everything is all right. We have f is given, but the integral that we want to do is on the circle. This. What kind of circle is that? Let us see that first. What kind of circle is x minus 3 squared plus y plus 4 squared equals to 4. What kind of circle is that? This is a circle with center. The center is x minus a number, so that's x component of the center. Y minus another number, because I have to have minus, so that's the center is 3 and negative 4, and radius is square of this, which is 2. So that's the circle. So if it is circle is closed, circle is simple, and it is positively oriented if and only if it is counterclockwise. But here the question says it is oriented clockwise. That means I cannot use Green's theorem until I deal with this orientation. But that is easy in our case because cy minus cosine y x sine y dr. That's my integral, the line integral we want to evaluate. This is the one we want to evaluate. The orientation is clockwise. I want to change the orientation. If you change the orientation in line integral for vector fields, you're going to end up with a negative sign inside on the right hand side. So this is equal to negative of, now everything is okay. Circle oriented in right way, left to right, and then the vector field is the same thing. I can write now. Okay, now we are in the left hand side of Green's theorem. I have to bring that minus down. It is equal to evaluate this double integral, which is over the disk inside the circle. Find partial derivative of this with respect to y, with respect to x. This is dq dx minus partial derivative of this with respect to y, which is 1 minus sine y dA. This is minus. These two cancel each other and I get negative dA. Okay. I have integral of d over dA. This negative signs cancel each other. What is that integral? Okay, I have a region. I'm integrating 1 over that region. That means it is equal to area of the region. It is area of the region. But what is the region? Region is a circle of radius 2, area of the circle radius 2. And you guys know that the area of a circle with radius r is equal to pi r squared. So in this case, the double integral ended up with an easy integral, and we could do the integration without doing actual integration because we knew what is the meaning of that. So just quick wrap up. The question was asked to evaluate this line integral, but the curve was closed, simple, not positively oriented. To make it positively oriented, I had to put a negative sign in front. Then when it is positively oriented, I can use Green's theorem. And this is equal to that. I have to bring this negative down. And then I end up with an integral which has a nice meaning. It is area of the region. The region for us was this. Area of this of radius r we know is equal to pi r squared. And that is the value of the integral for pi. Thank you for watching this video.